Now let's start with the differences between steady state and dynamic models. Let's go back to the same blending process example we had seen a few times in the previous lectures. Let's assume for a moment that the inlet flow rate of pure A is changed from an initial value of A to a final value of B. When that happens, it is going to affect the exit concentration X. Now the question that we want to pose is, for that particular change in the inlet flow rate of pure A, how is the exit concentration X going to change? One thing we can be certain of is that the initial concentration in the exit stream, D, is going to move to a new concentration, C, eventually after a certain time. But we don't know as of now whether that change is going to be smooth, if it's going to be oscillatory, or if it's going to be instantaneous. Depending on the process, depending on the dynamics of the process, depending on the type of differential equations that relate the different variables in this process, we're going to see one or the other type of response. It turns out that this particular process, the dynamics of this process can be defined by a single ordinary differential equation, and that ordinary differential equation, the solution of that ordinary differential equation, will never exhibit oscillations, and therefore the solution or the response exhibited by this process would be one that is denoted by the number 1 in the diagram here. There's an initial steady state, there's a final steady state, and a dynamic portion associated with this response. This is what we call a dynamic response, the dynamic response of the process. A steady state model simply relates the initial steady state to the final steady state. It has no information about how fast a process or a variable moves from its initial steady state to the final steady state. On the other hand, a dynamic model not only relates the initial and final steady state, but also the dynamic portion of the response. And this information about the dynamic portion of the response is essential to design controllers. To put it another way, a steady state model simply answers the question, by how much does X change for a change in the inlet flow rate of pure A W2? In fact, the changes in X and the change in the inlet flow rate of W2 can be related using a proportionality constant, K, which is shown here. On the other hand, the dynamic model answers the question, by how much does X change and how fast does it change to the changes in W2. There are different types of models. Steady state and dynamic models are, of course, two kinds of models. In this course, we're going to be mostly focusing on dynamic models because we want to control the dynamics of different types of processes. And within those dynamic models, one can consider linear models and nonlinear models. It turns out that most practical processes are nonlinear. However, designing controllers for nonlinear models or nonlinear processes is not very straightforward, and therefore we're going to be linearizing them and then designing controllers for the linear processes. Within linear and nonlinear models, there are theoretical models that one can build using physical laws or empirical models that one can build using the data. In this course, we're going to be focusing on the physical and empirical linear models that we can build using physical laws and data. There are some advantages to using theoretical models. Because theoretical models are developed using physical laws, they often tend to be very accurate. In addition to that, theoretical models provide very good physical insight into a process. If you understand the physics or the chemistry behind a process, it's very easy to develop an intuitive feeling, an intuition into how these processes behave. On the other hand, there are disadvantages to using physical laws. They're very expensive. Building models from physical laws is very expensive and time-consuming. In addition to that disadvantage, we also need to often estimate model parameters which are not readily available. Let's take a quick look at the blending process and develop a dynamic process model. Now, before you develop a model, it's always very important to identify and state very clearly all the assumptions, because the model, the type of model, the model equations will certainly change depending on the assumptions you make. And often you can complicate a problem as much as you want by not making the right assumptions. So if you make the right assumptions, right engineering assumptions, you can simplify the models. In this case, let's assume that the volume is not constant and that the concentration of P or A is exactly equal to 1, that the density of the liquid is a constant, and the work done by stirrer is negligible. These are rather straightforward and reasonable engineering assumptions to make. Now, there are three different mass balance equations that one can write for this process. One is the overall mass balance equation, and the other two are the mass balance equations on A and B. The overall mass balance equation is simply rate of accumulation in the tank equal to rate of mass entering the tank minus rate of mass leaving the tank, which is given by the differential equation in equation 1. We can similarly write mass balance equation on the component A, and that is given by equation 2. Now, because of the assumptions we have made, and because the density and the volume are assumed to be constant, we can bring or take those variables out of the derivative. Just on the side, I want to note that the mass balance equation on B is not required because B can be obtained very easily by subtracting the second equation from the first equation. The first two equations, equation 1 and 2, constitute what we call a dynamic model for the blending process. It turns out that we can simplify these two equations, and the simplification process is done in such a way that you have the derivatives on the left-hand side and everything else on the right-hand side. The simplified equation of equation 1 is an equation 1 star. The second equation can also be simplified similarly. However, volume V and X are both considered to be variables, and therefore that derivative has to be simplified using chain rule of differentiation. Once we do that and rearrange the different terms in the second equation, we get a simplified expression that includes only the derivative of concentration X and does not include the derivative of the volume. The derivative of volume is given by equation 1 star. These two equations, 1 star and 2 star, provide the dynamic model for the blending process, the simplified dynamic model for the blending process. So let's start with the independent variables and dependent variables. Independent variables are variables that are affected by process variables, other process variables, in the process of interest. Independent variables are variables that are not influenced by other process variables. Dependent variables are variables that are directly influenced by or affected by other process variables. Let's understand the difference between these two types of variables using a simple example. I will go back to the same blending process example because we will save time in reintroducing in introducing a new process. The process variables in the blending tank are X1, X2, and X, W1, W2, and W, and the volume. The independent variables here are X1 and X2, the two concentrations of the incoming streams. Note that X1 is not an independent variable to a process that is upstream of the blending process. For instance, if we have the tank on the left-hand side, for that particular process, X1 is a dependent variable. It is not an independent variable. In other words, the dependency or independency of variables depends on the reference process. W1 and W2 are two other independent variables with respect to the blending tank process. V, W, and X are the dependent variables because those three variables are influenced by other variables in the process. Dependent variables are also often the potential controlled variables. They are potential controlled variables. Now that we know the difference between independent and dependent variables, let's try to distinguish linear models from nonlinear models. There is a very rigorous way of proving whether a given model is linear or nonlinear. A lot of that rigorous mathematical details are provided in the textbook. If you're interested in the mathematical details, please refer to the textbook in Chapter 2. Instead, in this lecture, I'm simply going to give you three very important thumb rules that will allow you to identify whether a given set of differential equations that define a process are linear or nonlinear. So we consider a differential equation or an algebraic equation nonlinear if any one of the following three thumb rules are satisfied. If it contains product or division of at least two variables, for instance, if you have X over V, where X is the exit concentration in the blending tank and V is the volume, it is a division of two variables and therefore that term would be considered nonlinear. Or if it contains higher order, negative, or fractional powers of variables, x squared, x power half, or x power minus 3. Those are some examples. Or it contains functions such as logarithmic functions, trigonometric functions, or exponential functions. All those terms would be considered nonlinear, and hence any differential equation or algebraic equation containing those terms would be considered a nonlinear equation. Let's go back to the blending tank process. The process model is defined by two differential equations. We have derived these in the previous lecture. Now, equation 1 is linear because we have assumed that the density is a constant and therefore there are no fractions, there are no product of variables, and there are no trigonometric or logarithmic functions, and therefore equation 1 is linear. On the other hand, equation 2 is nonlinear because it has product of variables and also division of variables. W1 and V are variables. X1 is a variable, so you have product there and also division. Similarly, in the second term in equation 2, there are nonlinear terms, and therefore the blending process as a whole is also a nonlinear process. Even if you have parts of a process model that are linear, as long as there is at least one term or one equation in the model of a process that is nonlinear, then the entire process is considered to be nonlinear. It turns out that moving forward, we are rarely going to use the schematics of each process as we had done with respect to the blending process. Instead, we're going to represent every process with a simple rectangular block. The rectangular block here represents the blending process, and then we are going to use arrows to denote different variables that are affecting the process. In this case, X1 and X2 are the disturbance variables, W1 and W2 are the manipulated variables, X, W, and V are the controlled variables. Moving forward, we are also going to refer manipulated variables as inputs and controlled variables as outputs. Now, it turns out that process models, unless well specified do not have a unique solution. If a process model does not have a unique solution, then we're going to be in trouble because we cannot solve the associated differential or algebraic equations, and therefore we cannot design a controller. So when a process model is developed, it has to be well defined or well specified. The question we want to ask is, can we solve for the dependent variables in terms of the independent variables? Is that possible given the two differential equations we have for the blending process? In other words, can we solve for the two dependent variables v and x in terms of the independent variables, the w's and the x's? The answer, as it turns out, depends on what is called degrees of freedom. One can define degrees of freedom as follows. NF, the number of degrees of freedom, is equal to NV, number of variables in the process, minus NE, number of equations in the process. If NF, degrees of freedom, are equal to 0, we say the model is exactly specified and the model is going to have a unique solution. And that is similar to having two equations, x1 plus x2 equal to 1 and x1 minus x2 equal to 2, and wanting to solve for x1 and x2. Clearly, these two equations are independent and there is a unique pair x1, x2 that satisfies these two equations. Therefore, the model is well specified. Please note that x1, x2 in these examples are different from the x1, x2 used in the blending tank example. I'm just using arbitrary variables x1 and x2. Similarly, if the number of degrees of freedom are greater than 0, then we say the model is underspecified. In this case, in the case where NF is greater than 0, we have fewer equations than number of variables, and therefore we are unable to solve for x1 and x2 uniquely. If NF is less than 0, we say the model is overspecified because we have more equations than the number of unknowns. Most likely these equations are going to be inconsistent and therefore you will not be able to find a solution. If the model is underspecified, we need to add more equations to the model. If the model is overspecified, we need to remove a few equations or add more variables to the process so that the degrees of freedom are 0. If degrees of freedom are positive, then we need to specify certain independent variables. In a moment, it's going to be clear as to what I mean by specifying independent variables. If NF is less than 0, we will have to either drop equations or add more variables. So let's go back to the blending tank example and find the degrees of freedom we have. Let's assume that the variable V, the volume V, is constant. Then the number of degrees of freedom, NF, is equal to NV minus NE, which is equal to phi minus 2, and therefore we have 3 degrees of freedom, which obviously is greater than 0. What that means is, in order to solve the differential equations defining the blending process, we need to pre-specify at least 3 independent variables. And those 3 independent variables are W1, W2, and X1. If we can provide information about these 3 variables, in other words, if we know these 3 variables, we can add these 3 variables to the set of equations defining the blending process and therefore increase the number of equations in the model from 2 to 5. Once we do that, the number of degrees of freedom are going to be equal to 0. We're going to learn 3 main conservation principles. One is conservation of mass. The rate of mass accumulating in a system is equal to rate of mass entering the system minus rate of mass leaving the system. For instance, if you have an arbitrary system with a certain volume, you could have a number of variables entering the system, number of streams entering the system, and a number of streams leaving the system. In this figure here, W1 and W2 are the 2 streams entering the system, W3 and W4 are the streams leaving the system. We can apply conservation of mass and develop a differential equation that defines the dynamics of this system. rho times V is the mass, and its derivative must be equal to W1 plus W2 incoming stream minus W3 plus W4 outgoing streams. Now here is an example where I'm going to show you that it is very important to clearly identify the system around which you want to apply this law, this conservation law. So system 1 is tank 1, system 2 is tank 2, and system 3 is the overall system of both the tanks. Once you identify the boundary of your system, it is easy to identify the incoming and outgoing streams, and therefore you can apply the general law of mass balance. So for system 1 in this case, the rate of change of mass in system 1 or tank 1 is going to be equal to the rate of fluids coming in, W1 plus W2, minus W3, the rate at which they're leaving the tank. For system 2, similarly, there are only there's one stream entering, one stream leaving, and therefore on the right-hand side you will have W3 minus W4. For system 3, it's a bit more complicated because we have a recycled stream in the system. There's a stream coming from the outside of tank 2 back into tank 1. So to account for that, in system 3, on the right-hand side, you're going to have W1 minus W4 plus the recycled stream W2. So in addition to the overall conservation of mass equations, we can also write conservation of mass on species. If we have more than one species in the material you're considering, then you can write mass balance for each of those species. Rate of accumulation of species or component I is going to be equal to rate at which it's entering the system minus rate at which it's leaving the system plus the rate at which that particular component is being produced or consumed. Typically, when you have a reaction in a system, a component could either be produced or consumed in the reaction, and you have to account for that. So here's an example, a quick example. This is a simple CSTR, continuous stirred tank reactor, with two species entering the system, A and B, and two species leaving the system. Let's assume there is a reaction occurring in the system where A is going A is reacting with something else and forming a new product. In other words, A is being consumed in the reaction. And therefore, on the right-hand side of this conservation law, you're going to have W1x1, that is what is coming in, minus W2x2, what is leaving, minus the rate at which A is being consumed in the reactor. The third conservation law that we are going to learn in this course is conservation of energy. Rate at which energy is being accumulated in a system is equal to rate of energy in by convection minus rate of energy out by convection plus rate of heat addition to the process, either through an external process like a heating coil or through the generation of heat during a reaction, plus rate of work performed on the process. So let's look at a heating tank example. This is a very simple heating tank. There's an incoming stream, an outgoing stream. You're heating the material or the liquid that's coming in with a heating coil. Ti is the inlet temperature, Wi is the inlet flow rate, T is the outlet temperature, W is the outlet flow rate, Q is the rate at which heat is being added to the system. Cp is the specific heat per unit mass. Now, anytime a problem of this nature is given to you, it's very important to make certain engineering assumptions that make sense to you. Because without those assumptions, the eventual model could get quite complicated. Once you make the right engineering assumptions, the modeling exercise itself could be quite simple. So to make this process easy, let's assume that the stirrer mixes the liquid perfectly. In other words, there are no temperature gradients within the tank. It has constant hold-up. The volume is assumed to be constant. Let's also assume that the density of the liquid is constant and its specific heat capacity is independent of temperature. We'll also assume that the heater is properly insulated and therefore heat losses are negligible. And finally, the work done by the stirrer is negligible. if the stirrer is rotating at an extremely high speed, it is possible that it would transfer some energy, some significant energy to the system, and therefore result in an increase in temperature. So we're going to assume that that is not the case here. And because the volume is constant, the inlet flow rate must be equal to exit flow rate, and therefore Wi is equal to W. Now, using the conservation of energy equation, rate of accumulation of energy is equal to energy in minus energy out plus heat added, which is Q, plus work done, which in this case we have assumed is 0. The rate of accumulation of energy in the system is what is shown here on the left-hand side of the equation that I'm writing. The energy, the internal energy or the enthalpy of the system that is under consideration is rho times V times Cp times T minus Tref. Tref is a reference temperature. It's assumed to be constant, and it's arbitrarily chosen. So the left-hand side now represents the energy of the tank. Take its derivative, that gives you the rate at which the energy of the tank is changing. And on the right-hand side, we have enthalpy that is being added by the inlet stream. It's given by W1 times Cp times Ti minus Tref. And we subtract the enthalpy of the outlet stream from that and then add the heat input to the left-hand side. Notice that W1 is equal to W because of the mass balance equation, and therefore all the terms involving the reference temperature get cancelled. Anytime you derive an energy balance equation, the final version of that equation should be independent of the reference temperature you have chosen. So if you end up with some remnants of reference temperature in the final equation, you have most probably made a mistake in deriving the energy balance equation. Now let's perform quickly degrees of freedom analysis. There are three constant parameters in this model: rho, V, Cp. T, Wi, Ti, and Q are the variables, and there is one ordinary differential equation. And therefore, the degrees of freedom are 3, 4 minus 1, 3. And we need to specify three independent variables in terms of inlet flow rate, inlet temperature, and the amount of heat added to the process. By specifying these three independent variables, we will be able to solve the ordinary differential equation here. Now, let's move on to Chapter 2. We've learned how to build simple models using ordinary differential equations, using mass and energy conservation laws. Now, what I would like to do is introduce you to what are called Laplace transforms. This is going to be the topic of Chapter 3. It turns out that it is not straightforward or intuitive to understand the dynamics of a process purely from the differential equations. If you have a set of differential equations, it is not that straightforward to get an intuitive feel for the dynamics of a process. So for instance, if you have a differential equation, a first order differential equation, tau times dy over dt plus yt equal to ut. This is a simple equation, so we can find an analytical solution to it, but I'm going to use this simple equation to explain why we need Laplace transforms. Y and u are outputs and inputs respectively. Y and u are the two variables. Tau is assumed to be a constant. Now it's possible to use standard numerical techniques to integrate this differential equation and arrive at the solution y of t in terms of tau, the constant, and ut, the input. They are going to be some function of those two variables, tau and ut, would give you the output. That's one approach to solving the differential equation. Another alternative, intuitive, and much better approach is to use what are called Laplace transforms, which is going to be the topic of Chapter 3. Once we use Laplace transforms, the differential equation is going to be converted into an algebraic equation with no derivatives at all. Now in this case, the first order differential equation became tau s times ys plus ys equal to us, where s is the Laplace variable. We're going to be using these algebraic equations with Laplace variables, performing some simple algebraic manipulations. We're going to see that in Chapter 4, and arrive at an entity called transfer function. A transfer function is a relation between ys and us. we're going to learn later on in chapters 5 and 6 how to develop an intuition into the behavior of a process given its transfer function. From the transfer function, you can go back, use inverse Laplace transforms, and derive a time domain expression. So instead of taking the direct path between the differential equation to the time domain expression for the solution of the differential equation, we are going to be using Laplace transforms, converting the differential equation into an algebraic equation, which is then going to be further converted into a transfer function. We're going to study the dynamics of the transfer function. We will rarely go back to the time domain. Although it is possible to always go back to the time domain, we will rarely go back to the time domain. Instead, we are going to simply derive these transfer functions and develop intuition into how different types of processes behave to different changes in inputs.